Welcome to The Explainer. Today we are cracking open the secret behind, well, almost every poll you see, every quality check on the products you buy. It all comes down to this core idea called the sampling distribution. Let's dive in and see how it works. I mean, it kind of feels like magic, doesn't it? How can a survey of just 1,000 people possibly tell us what an entire country is thinking? This is the central puzzle of all statistics. And the answer? Well, it lies in these predictable patterns that hide behind random sampling. Okay, so to solve this puzzle, we first need to get our language right. You have to think of it like we're dealing with two completely different worlds: the huge world we want to know about and the tiny little world we can actually see and measure. So first up, you've got the population. This is the whole shebang. It's every single student at a university or every light bulb that comes out of a factory. The true values for this group, like the actual real average score of all students, those are called parameters. Just think of them as the fixed ultimate truth that we're chasing. Now, you and I both know we can't test every light bulb or survey every student. It's just not practical. So what do? We take a sample, a small, manageable piece of that population. And when we measure something in that small group, like the average score of our 500 students, that measurement is called a statistic. Right, so this is the absolute key difference you have to get. Parameters are the real, fixed truths about the big population. They're what we want to know, but they're usually hidden. Statistics, on the other hand, are the clues we get from our small samples. They change from sample to sample, but they're what we can actually calculate. The entire game of statistics is about using the statistic we can see to make a really smart guess about the parameter we can't. And this is where it gets really cool, because if every sample we take is going to be a little different, how can our statistics possibly be reliable? It just feels like total chaos. But as we're about to see, there is a stunningly predictable order hidden inside all of that randomness. Okay, let's just do a quick thought experiment. Imagine we go out, we pull a random sample of students from our university, and we calculate their average test score. And we get a result, 82.5. Okay. That's one data point. It's our best guess for now. But you know, what happens if we try that again? So what if we go back and do it all over again? We grab a completely different random sample of students from that same university, and we calculate their average score. And this time, we get 79.1. Whoa, a different sample gives us a different statistic. This is what's known as sampling error. And it's not a mistake, it's just a natural, expected part of the process. And that just brings us right to the heart of the problem. If our results are going to jump around like this with every new sample we take, how on earth can we possibly trust any single one of them to tell us the truth about the entire population? Well, here's the solution. The trick is to stop thinking about just one sample, and instead to imagine every possible sample we could have taken. The distribution of a statistic, like all those different sample means, across all those possible samples is what we call the sampling distribution. It's a theoretical map of every single result we could have possibly gotten. Okay, let's pause here for a second because this slide clears up one of the biggest points of confusion in all of statistics. The population distribution, that's the real truth we're after. A sample distribution, that's just the data from our one little snapshot. But the sampling distribution, that third row, that is the big, powerful theoretical idea. It's the distribution of a statistic if we took 1 million or 1 billion snapshots. This concept is the bedrock for everything that comes next. So let's focus first on the story of the sample mean. It turns out that its sampling distribution isn't random at all. In fact, it follows a very predictable script. And the key to unlocking that script is one of the most famous theorems in all of mathematics. So what are the rules of this script? Well, for starters, the distribution of all those possible sample averages, it's centered perfectly on the true population average. That's huge. And second, the spread of those averages is totally predictable. We even have a name for it, the standard error. And this is key, it shrinks as our sample size gets bigger. Simply put, more data means less guesswork. And now for the main event, the central limit theorem. This is the magic key. It says that no matter what the original population looks like, it could be skewed, it could be uniform, it could be anything, the sampling distribution of the mean will be approximately a normal, beautiful bell-shaped curve, as long as our sample size is big enough, usually around 30 or more. I mean, just think about how remarkable that is. It's like a universal law of statistics. We don't even need to know what the population looks like. As long as our sample is large enough, we get to use the nice, predictable math of the normal curve to make incredibly powerful and accurate statements about the world. It is the foundation of almost everything we do. So that's the story for averages, for means. But what about all the other stuff we measure, like percentages or proportions? You know, the percentage of voters who support a candidate? Well, it turns out that the exact same beautiful logic applies. The pattern for sample proportions follows a totally parallel script. It's centered on the true population proportion, and its spread, its standard error, also gets smaller as our sample size gets bigger. This direct link between sample size and error is exactly how polls can calculate and report a margin of error. It's not magic, it's just math. And you guessed it, just like with the mean, this distribution also becomes a predictable normal curve. The condition for it is just a little different. We just need to check that our sample is big enough to have found a decent number of yes answers and no answers. If it is, then the normal shape kicks in and we're good to go. Okay, so we've figured out that there are these hidden, predictable patterns in the results from our random samples. But why does any of this matter? This is the moment we finally bridge that gap from abstract theory to real-world confidence. And if you take away just one thing, let it be this. Sampling distributions are the bridge. They take the messy, random chance of pulling one small sample, and they transform it into a predictable, measurable science. Here's exactly how it works in practice. In the real world, we only take one sample, and we calculate our statistic. Then, we use that theoretical map, that sampling distribution we've been talking about. By seeing where our single result falls on this map of all possibilities, we can figure out just how likely or unlikely it was. And that is what lets us build confidence intervals and actually test our ideas about the population. Which leaves us with one final, powerful question. Now that we have this map, this predictable pattern of all the possible sample results we could ever get, how can we use it to attach a precise level of confidence to the result from the one and only sample we actually have? Well, that question, that opens the door to the rest of inferential statistics.